Today, we are going to finish part A from chapter 13. If you remember from back before spring break, we talked about the specific heat capacity for substances, and we used the formula Q equals mc delta T, where the Q was the amount of heat, M was mass, the C was a constant for different substances. That's called the specific heat capacity. And then we used delta T, which means the change in temperature. And so you had to figure out if did the temperature go up and what was the difference from starting point to end point, or did it go down, and that same idea. Today, though, we're going to go back to that idea of enthalpy. And I touched on it a little bit before we went into the idea of specific heat. So I'm going to go back into the notes and remind you of the definition of enthalpy and look at enthalpy of fusion and enthalpy of vaporization. Then we're going to look at a problem where you're going to combine specific heat with the enthalpy of fusion and the enthalpy of vaporization and see how that kind of works, just talking about it with ice cubes melting. Then we're going to go into talking more about enthalpy and enthalpy of formation, and how you're going to use a table in your book to work on some problems with that. That we will finish section A today, and then on Thursday, you'll have a quiz only on section A. Okay, so let me pull up the notes. Let's review some enthalpy problems. Oop, that's biology. Here we go. Oh, let me present. Sorry, hang on. Okay, here we go. So just to review, we talked about this idea of sensible heat and latent heat. And if you were, just a quick reminder of that, sensible heat is when you have a temperature change in the substance. Latent heat is when the temperature doesn't change, but you're going through a phase change in your substance. All right, so the melting process is occurring, or the evaporation process is occurring. So there's no temperature change, but you're in the process. This entire process is evaporation from this point all the way to this point. So you're adding energy, you're adding heat here, but there's no temperature change until that last drop of liquid has evaporated, and then the gas can increase in temperature. So a quick review on this. We defined this last time, but the molar enthalpy of fusion, a lot of times now we'll just use this heat of fusion as well as just another way to describe it. That's how much energy is required to melt 1 mole of a solid to a liquid. All right, and you don't involve temperature change with that. And then you have the same idea, but it's heat of vaporization, delta H with the subscript of VAP. Then that's the same idea, except you're converting 1 mole of a liquid to its gas. And again, you're not going to see a change in temperature. And there's a table in your book with these values for selected substances. You can look online or any number of tables that are available. So you don't have to calculate those. You just have to know how to use them. All right, now putting that into practice, let's come down to this graph. So here's an entire process. We start down here with ice. All right, and we're not, there's no thermal energy there, and the ice is cold down to -20 degrees Celsius. Well, eventually we're going to add some energy to this system. And as we add enough energy, we're going to get to 0 degrees Celsius. But that's still a freezing point of ice. So keep that in mind. So we still have ice. But if we continue to add energy, that ice will melt. Now notice what happens again, just as a review, that temperature doesn't change. But we're adding energy. And so as you start with the block of ice or however much ice you have, you begin the melting process, the temperature stays the same. But then once all of the ice has melted, you can continue to add energy, and your temperature of your liquid now will begin to increase. and that will increase, and it will increase as you add energy. Now look, it doesn't take that much energy. We're going to add all of that, and we're going to get up here to the boiling point. This is water, remember. So the boiling point of water is 100 degrees Celsius. Once we reach that point, the temperature doesn't change. Then we stay at this temperature until every last drop of liquid has evaporated. Then the temperature is allowed to rise again when everything's a gas. So let's turn that into a problem. All right, how much energy is required to melt and then vaporize 5 grams of ice while the temperature increases from 273 Kelvin or 0 degrees Celsius to 373 Kelvin or 100 degrees Celsius, so the freezing point and the boiling point of water. All right, so here we go. We have to use multiple values. We have to use the heat of fusion, the specific heat of water, and the heat of vaporization because we're going through a melting process. We're going through where you're just needing to use the specific heat. And then we have to take into account the heat of vaporization, how much energy is required to vaporize 5 grams of now water. All right, so here's where this starts. Look at this point number 1. See, nothing really is calculated here because we're just in the ice phase. All right, but here we start to melt. Well, that's the idea of fusion. All right, so we're going to look up the delta, the enthalpy change or the enthalpy of fusion, which is the energy that's going to be required to melt 5 grams of ice. Now, here's what you have to do first. I take that 5 grams and I'm going to divide it by the molar mass because if you look in the table, you will notice that the units are kilojoules per mole. The units for heat of fusion are kilojoules per mole. Well, I don't have moles, I have grams of ice. So the first thing, once I use the enthalpy of fusion or the heat of fusion, I have to convert to moles first. So that's what I do here. I'll take 5 grams, divide it by the molar mass of ice, which is 18.02 grams per mole, and then I get moles of water. Okay. Then I look up the heat of fusion for water, or ice rather, so that's 6.01 kilojoules per mole. I just looked it up in the table. So then I multiply, I have 0.277 moles of water because I started with 5 grams, converted it to moles, and then I multiply that by the heat of fusion, and I get 1.66. Now notice the units, kilojoules. That's important. We got to keep up with that because step 2, notice that this point, we are not melting anymore. We have all of our ice is now a liquid. So we need to then determine, remember, the sensible energy required to heat water from 0 degrees Celsius or 273 Kelvin to 373 Kelvin or 100 degrees Celsius because you have to heat up all of that water before you can reach the boiling point and start to evaporate. So now we go to our specific heat capacity. Q equals MC delta T. All right, so we know we have 5 grams. Look, I don't have to convert because my formula says mass. So Q equals MC delta T, so 5 grams, and the specific heat of water is 4.18 joules per gram times degrees Celsius. And then that gives me my energy in joules. So I just took 5 grams given to me in the problem. Oh, and let me fit in right here. Hang on, sorry about that. I need to multiply this by what? 100, because my temperature is going up 100 degrees Celsius. Okay, so then, there we go. So I've got my mass, I've got my C, and then I have my delta T. So that requires 2,090 joules. But look, I need to keep my units for energy consistent, and I have kilojoules up here. So what I'm going to do is I'm just going to change these joules to kilojoules. So I divide by 1,000, and I get 2.090 kilojoules now. right here. Last step, number 3, look, I'm not changing my temperature anymore, so I can't use specific heat. There is no delta T. Delta T would be 0. So I can't, that doesn't tell me anything. That's not really what's happening. So, oops, sorry, let me get that back. So now I'm vaporizing. I'm boiling. So all of my water is going from liquid to gas. So I'm going to use the heat of vaporization. So again, same idea. I have to convert, because if you go and look up the units for heat of vaporization, you'll see that it's kilojoules per mole. Well, again, I was given grams in my original problem, but I know that that's 2.77 moles. So I'm going to look up the heat of vaporization, which happens to be right here, 40.7 kilojoules per mole. I multiply that by 0.277 moles of water, and then I get 11.3 kilojoules. Okay, so everything now is in kilojoules. So the final answer for this would be that I take 11.3 kilojoules plus 2.09 kilojoules plus 1.66 kilojoules. And that would, so basically I'm adding step 1 with step 2 and step 3. That is my total amount of energy required. So if I do that, let me check my calculator. I'm going to add 1.66 plus 2.09 plus 11.3. And when I do that, I find that it's 15.1 kilojoules. So it takes 15.1 kilojoules of energy to melt 5 grams of ice, then to let it heat up to boil, then to vaporize all of that water requires 15.1 kilojoules. Okay, so that's using heat of vaporization or enthalpy of vaporization and heat of fusion or enthalpy of fusion. Now let's talk about a different kind of enthalpy. We're going to talk about the enthalpy or the heat of a reaction. Now, this is an entire chemical reaction we're talking about. Now, up there, in that last example, we were only talking about phase changes. We started with water, we ended with water. Now, let's take it to where we're actually doing a chemical reaction, and we're going to make water. All right, here's the deal. You have the delta H, the change in enthalpy. We want to know how much energy is being released or has to be taken in to a reaction in order to make it work. So you're going to, and when we're talking about the heat of a reaction, you're going to look at the enthalpy of the products, subtract the enthalpy of the reactants. All right, and so this is how it would work. The good news is, again, you can look up these values for enthalpy of each of these individual things. All right, so let's look. You don't have to calculate the enthalpies. You have to know how to use them. That was my point. So if we're going to make water from its elemental forms, now you don't really do this. It's not very practical because water is so readily available. But if we were to do that, we would take hydrogen and oxygen and make water. That process, notice that it's balanced. That's going to be very important, and I'll tell you why in a minute. We balance the reaction. When you do that, when you see how this says it's a plus, so you have water plus 571 kilojoules, that means that it's giving off heat. Heat is basically a product of this reaction. So if it gives off heat, that means it's exothermic. Okay? If heat is a product, it means it's overall, it's giving off energy, a net release of energy between the reactants and the products. All right, so let's talk about what all that means. So you'll go back to this equation and notice that on the on the product side was energy. 571.6 kilojoules of energy is released if we were to make water from its elemental form. So let's talk about what that means. All right, so in an exothermic reaction, that means that the reaction overall gives off heat, gives off energy. The products have a lower enthalpy than the reactants. So let's go back to that equation. Does that make sense? If you give off energy, that means your products have less enthalpy than your reactants do. And what happens is you get, look, but it's still always products minus reactants. It is not big number minus little number. So you have to take your products, subtract from your products the heat of reactants, and sometimes you'll get a negative. When you get a negative delta H, that means it's giving off energy, and it's exothermic. Okay, we'll talk more about that. If you have an endothermic reaction, that means energy is put into the system in order to make it go. The products end up with a higher enthalpy than the reactants. And again, let's go back. If the product value, the delta H value or the enthalpy value is greater than the reactants value, then you're going to get a positive number. That means it's endothermic. It's an endothermic process. I'm going to show you this on a graph, but pay attention. Let's review this one more time. The products, meaning what's made in an exothermic reaction, have a lower enthalpy than the reactants, and energy is released. The products in an endothermic reaction have a higher enthalpy than the reactants because energy gets absorbed. Now let's look at this in a graph form. Here is the example of an exothermic process. We start with our two reactants, hydrogen and oxygen. This was the thing we just looked at. Notice the reactants, as far as energy content, start up way up here. Now, it's like a little roller coaster. All right, you start with the hill, it's just a slight hill. But then whoosh, when that reaction goes, you go down a steep hill, and that's the fun part of the roller coaster, right? And you make water, but notice your products have much less energy, because here's the energy content on your y-axis. This is just time, basically, how the reaction progresses. So water has much lower energy than the reactants you started with. Notice the delta H here is negative because the formula to calculate delta H is the products, delta H, the H of the products, minus the enthalpy of the reactants, or the H of the reactants. So if you start out low, just think about basic math. If you take a lower number and subtract from that lower number a higher number, you're going to get a negative number. 2 minus 5 is negative 3. Same idea, except for dealing with bigger numbers than 2 minus 5. All right. Likewise, or conversely, I should say, if you have an endothermic process, now we can't use this process over here, excuse me, because that's exothermic. So we're going to change our reactants in this equation. We're going to take carbon and hydrogen. Those are reactants that we're starting with. Look up here at the product, C6H6. Look, the products end up higher. This is not a very fun roller coaster. Look, it requires a whole lot of energy to get going, and then wah, wah, just a little bit of a hill. Okay, that is not a fun roller coaster. So your products end up with a much higher amount of energy than your reactants. So it's endothermic. You have to put a lot more energy into this reaction to get it to go. All right. So you see here, there's a positive enthalpy because the products minus the reactants, products, higher energy, so higher number minus lower number gives you a positive. So let's go with the opposite reaction or example. So 5 minus 2, higher number minus a lower number gives you a positive 3 value. So you end just like this. All right, a positive value there. Okay, how are you going to use this? What can we do? We're going to use this to talk about enthalpy of formation. Now, go back briefly, jog, go back to your brain, pull it out. What did we talk about when we dealt with gases? What was our standard, that STP value? Do you remember that? First of all, what did it stand for? Standard temperature and pressure. 1 atmosphere was standard pressure, but do you remember what the temperature was? I think it was 0 degrees. Okay, when we talk about enthalpy, we're talking about not STP, we're talking about something called standard state. Now, why? Well, 25 degrees is kind of considered borderline normal temperature. So when we talk about the heat of formation, we don't want to talk about things that exist at really cold temperatures like 0 degrees Celsius or really high temperatures. We want standard state, like how things normally appear to us as we live on the earth generally. Now, sometimes, yes, it gets cold and we get snow. But how would things appear at normal conditions, which is considered standard state, 25 degrees Celsius in 1 atmosphere? So, for example, gold. How does gold appear at, think about it, room temperature, basically, 25 degrees Celsius? It's solid, right? So when we talk about, and water is liquid at standard state. So when we talk about these enthalpy of formations, basically how much energy is required to form the substances we're going to talk about, we're going to be dealing with them in their standard state. So whatever it is at 25 degrees Celsius and 1 atmospheric pressure, which is what you live at, 1 atmosphere pressure, that's the state of matter that we're going to use for these calculations. So here we go. When we talk about the standard molar enthalpy of formation, what that means is the enthalpy change, so delta H, whoa, where's my cursor? There it is, delta H, so change, the enthalpy change for the reaction that produces 1 mole of a compound in its standard state from its elements in their standard states. All right. Most values of delta H of formation are negative. What does that mean? It means they're exothermic. So that means when they are made, energy is given off. So here's a way one of these problems would be approached. Here's the question. What is the delta H of formation for nitrogen plus oxygen? Notice my equation is balanced. To form NO2. Again, equation is balanced. All right. The reason it has to be balanced is because it matters as a mole ratio. So look what happens. Let me give it a little space. So we have nitrogen, oxygen forming NO2. Balance it with a 2 here, a 2 in front of the oxygen, and then the 1 is understood for nitrogen, and it's balanced. Now, this is a pretty easy problem because think about this. Nitrogen in its elemental form, oxygen in its elemental form, they have a heat of formation of 0. So you don't have to include them in your calculations. Now, why is that? Think about this. Standard state. How does oxygen normally appear? What is its standard state? Its standard state is O2. The standard state for nitrogen in the atmosphere is N2. That's just how they're made. That's how they exist. They're elemental that way. So any elemental substance, whether it's N2, O2, or just say like gold, the heat of formation, is 0 because they already exist. That's how they just exist. So it doesn't require any energy to form them because they're just elements. They just are. So anytime you see a problem where you're dealing with some elemental substance, you could assume it's 0, but let me also tell you, you don't have to assume, because you're referring to this table in your textbook. There is a table in this in chapter 13. Let me find it. It's 2 pages long, and it has the heats of formation and various other things too. But it has the heats of formation for multiple substances, both elemental and compounds. So, but I will show you that when I look up on this table, there's a 0 there. And you'll go to these to solve these problems. The table is on page 352 and 353. So the heats of formation, you can see like silver, 0. Barium, 0. Carbon, 0, because it's in its elemental form. All right, so any substance in its elemental form is 0. Nitrogen, N2, oxygen, O2, that's how it exists on the earth naturally. So that's the heat of formation is 0. It doesn't require any energy to form that because it just is. So the only thing we have to worry about, so going back to that formula, products minus reactants, well, our reactants are 0. Nitrogen 0, oxygen 0. So we don't have to worry about those, but we do need to worry about NO2. So going back to that table, I'll look up the heat of formation of NO2. Okay, the heat of formation of NO2 is 33.2 kilojoules per mole. Now that per mole matters because so that's where I go back and look at my balanced equation. 2 moles of NO2 times 33.2 kilojoules per mole gives me a heat of formation of 66.4 kilojoules. And again, I did not have to worry about the heats of formation of my reactants because they're 0, because that's how they appear normally. Okay, any pure substance is like that. Formation. Sometimes we're going to look at combustion, but it's the same thing. The idea is the same. It's when any reaction involving oxygen, remember, go way back to first semester, is a combustion reaction. Okay, but the idea is the same. It's the energy, the heat of combustion, has a C there, is the energy released as heat when you completely burn 1 mole of a substance at standard conditions, which remember is 25 degrees Celsius, 1 atmosphere. All of these values are exothermic because burning is an exothermic process. Now, when we start calculating a reaction, we're going to look at 2 chemical processes because each reactant, in order to react with something else, has to break down into its elemental substances. And then they react and recombine to form the new. So it kind of looks something like this. So if we were to react lead 2 oxide and carbon monoxide to form lead and carbon dioxide, it would look something like this. So here is one of my reactants, lead 2 oxide. Here's my other reactant, carbon monoxide. And you will see here that they break apart. As the chemical reaction starts, lead and oxygen have to break apart. Carbon and oxygen have to break apart. So you see we have the 2 oxygens, the lead and the carbon. Then they all react chemically to go into form lead and carbon dioxide. Now, you do your heat of formation or your heat of the reaction problem, and you look. So lead, it's an elemental substance. Its heat of formation is 0. All right, and then you come down and you look for the heat of formation of carbon dioxide, which is negative 393.5 kilojoules. All right, so you take these into account. You do your reactants minus your products, and you get negative 65.7 joules. It's negative. This reaction gives off heat, so it's exothermic. All right, now there's one law that we need to talk about, which is Hess's law. Now, it doesn't matter if you're using combustion or formation, if it's, you're going to use the Hess's law, which is the enthalpy change of reaction equals taking all the enthalpy changes for each step of the process. So you take the heat of the products, delta heat of formation of the products, you add it to the heat of formation of the reactants, and that gives you Hess's law. So if you look in your textbook on page, sorry, page 344, you go through this process of Hess's law. So you're adding, it's the sum of the enthalpy changes for each step of your reaction, which is and that gives you the overall heat of your reaction. So how are we going to do this? Hess's law works. You may use any balanced equation, but if you look at the opposite direction, meaning like go back to that initial chemical equation where we have hydrogen plus oxygen gives you water. The reverse, if you were to decompose water, that would be you would have to switch around your sign. So it would become an endothermic reaction. So you could use any balanced equation for Hess's law, but it has to be balanced, number one. And you have to change the sign if you reverse and your reactants become your products. All right. Then the other important thing is you have to have a balanced equation because you have to use those coefficients because it's a molar ratio. So you multiply the coefficients of a balanced equation to get the desired equation, but you have to multiply the delta H by that balanced coefficient. So let's look at an example. I know that's a lot of words. I think it'll make sense when we put it to practice. Okay. Oops, let me do some editing real quick here. We want to find the enthalpy for the combustion of methane. And we're going to use the standard enthalpies of formation. So we're going to have to use that that table that took up 2 pages. All right, again, as a reminder, that's on page 352 and 353, right here. Okay, so we want to combust methane. Methane's that stinky gas that you smell in swamps or around cow pastures, and you're going to combust it, and it's going to give us carbon dioxide and water. So what I'm going to do is, first of all, make sure I start with the balanced equation. Now, hint, I went ahead and balanced this for you. It is balanced. But notice I've got the molar ratio is 1 mole of methane, 2 moles of oxygen, giving me 1 molar carbon dioxide and 2 moles of water. So I'm going to sum up my products. Then to get my change in enthalpy, I'm going to sum up my reactants as well, and I need the change. How much energy is exchanged in this process? So I'm going to take my products, add them all up, subtract that from the sum of my reactants. So here we go. All right, so if I look up, so first of all, pay attention. In my products, I have water as a liquid, standard state, water as a liquid, and carbon dioxide, standard state, as a gas. So I go to the table in the book, all right? I pay attention to my coefficients. So when I look at the table of the book for carbon dioxide, I will see that my heat of formation is negative 393.5 kilojoules per mole. I have to multiply that by the understood 1 mole to cancel out the moles. Then I'm going to add that value to the heat of formation of water as a liquid. And again, I don't know this. I look it up in my table, and I find that it's negative 285.8, again, kilojoules per mole. But this time I have to multiply that value by 2 because that's what my balanced equation tells me to do. So notice I've enclosed this in parentheses because these are my products. I'm going to do that math, and I'm going to say negative 393.5 times 1 is negative 393.5. I'm going to add that to 2 times negative 285.8. That gives me the sum of my products for their heats of formation. Then I come over here and I do the same thing with the reactants. So I go and I look up methane. Methane is, there's only one based on a balanced reaction. I have 1 mole as my ratio times negative 79.6 kilojoules per mole. Now look at this. Remember, enthalpies, heats of formation for elemental substances is 0. And if you don't believe me or if you don't trust that, You don't trust your instincts on that, look in the table. But it will tell you, if you look up the heat of formation, it's 0 kilojoules because it's elemental, it's standard state. That's how oxygen is. It just exists like that. So when I add this up, 1 times negative 79.6, well, 0, I just get negative 79.6. And then I have to rely on my math skills. So pay attention, negatives matter here. Pay attention to how you put it in the calculator. While you're watching this at home, please make sure when you do this math that you get negative 885.5 kilojoules. If you don't, figure out what you're not putting into the calculator correctly, or come talk to me at office hours, okay? Now, that is the end of the enthalpy problems. I've given you an assignment on Google Classroom. So your quiz is on Thursday, and it's covering the specific heat problems, and it's going to cover these enthalpy type problems. But you've got several to practice today. So practice these today. Email me with questions. Come to office hours either on Tuesday today or on Wednesday to get these questions answered. Okay. One thing I want to tell you, as you refer to this chart on page 352 to 353, there are several different things. We haven't gotten to everything that's discussed yet. That's coming. So as you look at this chart, if you look on page 352 to 353, you'll see there's several different values. You'll see the delta H of formation. That's what we're using today. But then you'll see an S, which stands for entropy, which we'll get to tomorrow. And you'll see delta G, okay? So make sure today, for each of these substances listed, you use the first column, the heat of formation. All right, we will get to entropy, which is S, and then we'll get to delta G, which is Gibbs free energy. That's all coming in the next couple of sessions, okay? Make sure you use the right column. All right, that's it for today. Practice these problems. Come see me during office hours, and I will talk to you guys soon.